Hey, let's take a look at number 5 in section 10.6. We're going to find the interval of convergence for this power series. So first of all, note that this is centered about x equal 2. Clearly, it's going to be convergent, right, if x is 2. So what if x is not 2? What can we do? Well, let's take a look at the ratio test, right? Remember, we take a look at the limit as n goes to infinity of this ratio. Take the absolute value of those terms. Of course, these terms of course, depending on x, right, these terms could be positive or negative, so we want to be careful about that. Um, so a sub n plus 1, again, just replace n with n plus 1. I'll get x minus 2 to the n plus 1 over n plus 1 to the ninth plus 2. And then dividing by a sub n is the same as multiplying by the reciprocal. So the reciprocal of a sub n is here. I've gone ahead and divided numerator and denominator by x minus 2 to the n. Right up here, that leaves one x minus 2 factor. I cannot do any really canceling here, okay? And I don't want to try and expand this all the way out and see if I can find a common factor. That's not going to help, and that's going to take too much time, so we don't really need to do that actually. Um, let's take a look at this limit. If I take the absolute value of x minus 2, right, that's really a constant in terms of n, right? N is going to infinity. X is not affected by the value of n for any given value of x. So I'm going to pull that as a constant multiple, provided this limit exists here, which is up top n to the ninth plus 2, and on the bottom n plus 1 to the ninth plus 2. So what's this limit going to be? Well, I hope you can see if I were to expand this all the way out, which I'm not going to do, but the highest degree term I hope you see will be n to the ninth. And then I'll have something n to the eighth, something n to the seventh, and so on. These will all be degree 8 or less. The last one will be 1, right? And then 1 plus 2 is 3. So all these terms are less than degree 9. They're 8 or less in degree. And therefore, I hope you see that this limit will just be equal to the ratio of the leading term coefficients, right? Which is 1 over 1 or 1. So the limit as n goes to infinity of all this stuff is 1. And you could, of course, use L'Hopital's rule to think that through several times, and you can see you would get 1, but we're not going to go through all the details. Hopefully that makes sense. So the bottom line is this limit is just the absolute value of x minus 2. So remember the ratio test, in order for the series to be absolutely convergent, this must be less than 1, which forces x minus 2 to be between negative 1 and 1, which adding 2 means that x is between 1 and 3. So it's absolutely convergent for all values between 1 and 3. Now what do we need to do? Check the endpoints. So we're centered about 1. Our radius of convergence is 2, right? And so what about at x equal 3? Well, if I plug in x equal 3 to our original series, 3 minus 2 is 1. 1 to the n is always 1, so I just get 1 over n to the ninth plus 2. Get this series. Now, does this series converge? Well, 1 over n to the ninth plus 2 is always less than 1 over n to the ninth for all n greater than or equal to 0. Notice we're summing from n equals 0 on. And that's because the denominator of the fraction on the left is more than the fraction on the right. Therefore, the fraction on the left is actually less than the fraction on the right. Also, if we look at this, the terms here, if we look at the series n equals 0, I guess we'd have to go from n equal 1 to infinity of that series, right? That's going to be a convergent p series, right? So we know that converges. Our terms are always less than the terms of a convergent series. Therefore, our series converges by the direct comparison test. All right, what about x equal 1? Well, if I plug in 1 up here, 1 minus 2 is negative 1. I get negative 1 to the n. Well, negative 1 to the n over n to the ninth plus 2. Well, this is going to be convergent by the alternating series test. We have an alternating series. The a sub n, the absolute value of the terms would be 1 over n to the ninth plus 2. And clearly the two things we have to show for alternating series test, number 1 is that the limit as n goes to infinity of a sub n is 0, and that is definitely true. We can see that, I hope. And then number 2, we have to show that a sub n plus 1 is always less than or equal to a sub n, and that's going to be true. If we look at a sub n plus 1, that'll be 1 over n plus 1 to the 9th plus 2, whereas a sub n is just 1 over n to the 9th plus 2. And so notice, you got the same 1 in the numerator, you got the plus 2 is the same. The only difference is n plus 1 to the 9th versus n to the 9th. Notice this will always be 1 more to the 9th versus this one. And so this denominator is always bigger than this fraction. Again, this fraction is always less than that. The fraction on the left is always less than that one. So these two things being true, and with that sign changer, we have convergence by the alternating series test. Bottom line is both of our endpoints, the series converges, so we do want to include those. So we're going to use brackets on those endpoints of our interval. Okay, that's the interval of convergence. Hope this helps.